So welcome back. Let us continue our discussion of application of group theory to spectroscopy. And in that topic, we were discussing what is spectroscopy, and we finished discussing rotational spectroscopy. So let us now discuss vibrational spectroscopy. Again, this is not a comprehensive discussion on vibrational spectroscopy. This is just an overview. So we will not be deriving any equations. I'll just be giving you some information on what vibrational spectroscopy is so that when we use the application of group theory, you know what it is. Okay. So vibrational spectroscopy, as from the name, it basically looks at the vibrating bonds. So let us consider for this spectroscopy, let us consider a molecule CO2. Okay. So CO2 structure is, let me draw the structure like this. So I'm not drawing the complete bonds and all. So delta negative will be here, delta negative will be here, and two delta positive charge will be here, right? So if you look at the overall dipole moment of this molecule is 0, right? So that means no pure rotational spectrum can be observed. We have discussed that, right? Because there is no dipole moment, no electrical component of the EM wave cannot interact with the dipole moment component as the molecule is rotating. So no pure rotational spectrum is observed. Now what do we do if we want to characterize the physical properties of this molecule? So even though the dipole moment is 0, but the change in dipole moment as the molecule vibrates, that is possible to observe. So what do I mean? So what I mean is, let us say this is the equilibrium position of the molecule. Now there can be a stretching which looks like this. See, again, all these molecules can be described by ziggling and wiggling of atoms, right? So no two atoms will be at constant position. It is not a rod which is tying the two atoms together, right? They will be constantly moving, and this will lead to vibrations, right? So again, it will go to its mean position, and now the other carbon oxygen bond may stretch, and again it will go back to its mean position, right? So now if I try to draw the component of this dipole, it will look like, so the dipole is 0 over here. So these are vibrations, and the dipole moment looks like this. So dipole moment is 0 here. I can say that the direction is downward here, 0 here. Again, direction of the dipole is upwards, 0 here again. So again, it is following a periodic motion if you look at the vertical component of the dipole moment, right? So I can say the component of the dipole, component of the dipole. So it will be 0 at this point, then negative at this point, 0 again, positive, 0. So you can see that there is a sine wave which is being formed, right? Something like this. So now again, the frequency of light that interacts with this dipole component is in infrared range. So you can also visually think or intuitively think that if the rotation is happening, the rotation would take lesser energy as compared to vibration of a bond. So vibration is trying to overcome the two attractive forces here, and it is trying to pull away the two atoms. So this requires more energy. So that's how it goes from microwave to IR range when you go from rotation to vibrational spectrum, right? So vibrational spectroscopy can be understood when you, again, let us consider a diatomic molecule. So we can say vibrational spectroscopy can be understood by starting with a simple harmonic model. So what is a simple harmonic model? So what you have is, see, in case of rotation, we considered two atoms connected with a bond where the vibration was not considered, right? It was a rigid bond, like a rod. But here we are considering two atoms with a bond which is where the vibration is possible. So what do I mean by vibration? It's like if two masses m1, so these are atoms and this is my bond. But if I'm considering that there are two masses m1 m2 and they are connected with a spring, something like that, right? So now you can compress the spring, you can stretch the string, and then you can allow it to freely come back to its mean position, right? All that can happen. Now all of this will change the energy of this system, right? So how do I describe this change in energy? I can always say that if I plot energy here and let us call the mean distance as r here. So at the equilibrium distance, the energy will be minimum, right? Now as I start to stretch, the bond length will increase, right? So this is my bond length and the energy will increase. So it will go like this, right? And now as I start to compress, again the energy will increase. It will go like this. So this is called as a simple harmonic model. So either way you go, the energy will increase. So this side is compression of the spring or the bond, and this side is stretching of the bond or the spring. And this particular plot is called as potential energy surface. So this is compression, stretching, and potential energy surface. And now if you want to actually look at the equation, so for, we can say, for harmonic oscillator model, so harmonic oscillator model to represent a diatomic molecule, we can say the potential is equal to half. It's a equation of a parabola, right? The potential is in the form of parabola. So I can say this is half kx square, right? This is equation of a parabola. So you should all be aware of what is a parabola. So what is K here? So K is bond force constant, very similar to spring constant, right? Which you must have read in physics in maybe class 12th. So Hooke's law is considers the spring constant, right? When you look at the Young's modulus and all. Okay. So X here is R minus R0. So which is, so R is internuclear distance. And at a given time. and R0 is the internuclear distance at equilibrium. So that means X is the difference from the mean position. If this is my mean position, I would call this as R0. So any deviation from R0 will be called as X, because R is the absolute value at a given point, right? Okay. So now for quantum systems, not all energies, all vibrational energies are not possible. Not all, we will say, energies are possible. And the only possible vibrational states, the possible vibrational states are given by vibrational quantum number. V. Okay. So this is V, and then energy of a particular vibrational state will be given by EV is equal to V plus half into H nu. Now do not get confused between V and nu. So V is the vibrational quantum number and nu is the fundamental frequency. So we'll write nu as the fundamental frequency. So we can also write an expression for nu. Nu is given by 1 over 2 pi square root k by mu. And we have already seen what is k. K is bond force constant, and mu is reduced mass. Reduced mass also we have discussed already in rotational spectrum, right? So selection rule for vibrational spectroscopy is delta V should be plus minus 1. So you can only carry out transition between V equal to 0 to V equal to 1, or V equal to 1 to V equal to 2, and so on, right? So what we can say is, we can say delta E V to V plus 1 can be written as V plus 1 plus half H nu minus V plus half H nu. So this comes out to be H nu only, right? V plus half will get cancelled, so 1 H nu. Or we can say delta E divided by Hc, and you can call it in nu bar, right? So this is wave number, and the units are centimeter inverse, right? So typically in spectroscopy, sometimes wave numbers are used, sometimes lambda is used, but typically in vibrational spectroscopy wave numbers are used, so that's why I've written it like wave number. Now the kind of transitions which are possible, let us try to draw. So in case of harmonic oscillator model, if you notice that delta E is equal to H nu or nu bar, so that means from it can be V equal to 0 or V equal to 1, starting from V equal to any given thing. So this is V equal to 0, V equal to 1, V equal to 2, V equal to 3, and so on. Now the transitions which are possible are V equal to 0 to 1, 1 to 2, 2 to 3, 3 to 4. These are all allowed transitions. So I will write down here all allowed transitions. And how do you know what transitions are allowed or not? So we have already seen that by looking at this integral where we say that the wave function of a particular vibrational level, and then the operator and wave function of v plus 1 level and star and d tau. So if I is not equal to 0, transition is allowed, right? So this part you can actually look at the character table and find out uh, what are the irreducible representations. We have already done that, so let's not go into those details. So this is basically called a simple harmonic model, but there are problems with simple harmonic model, right? So what are the problems? Let us discuss that. Problems with simple harmonic model. So first of all, it defines that all energy levels are equally spaced. That means all the spectral lines will come at exact same position in frequency, right? But you do not see that. You do see multiple lines. Of course, it will all depend on the population distribution, that which line will be more intense, where the population difference will be maximum, and so on and so forth. But they do appear at different frequencies. So the simple harmonic model does not explain the multiple lines in the vibrational spectrum, because it predicts that all the lines should have equal energy, and hence all of them would come at same energy level or same frequency number. So all energy levels are equally spaced. That is a problem. Second problem is equilibrium bond length is constant for all energy levels. So what do I mean here by saying equilibrium bond length? So if I look at the equilibrium values over here, it is something like this, right? So at v equal to 0, or at a particular stretched state of a bond, my R0 is here. If I extend my bond, again my equilibrium bond length is still the same, equilibrium bond length is still the same, which does not describe the vibration, because like if the vibration is happening, there is a stretching which has happened, so the equilibrium bond length should change, right? Now the simple harmonic model does not explain that. Okay, so it also does not account for possibility of bond dissociation. So does not account for the possibility of bond dissociation. So that means no matter how high a vibration is happening, it will never break, which is not true, right? If you vibrate a bond very, very high frequency, it will eventually break down. So this particular model does not explain that, right? So that means we have to do some adjustment to this model. So another factor which the model does not explain is the extra repulsive force at very small bond lengths. That means if I'm going down in the bond length, I have not written what is what here. So this is R and this is E. So if I go down in the bond length, it does not explain basically that the nuclear fusion reactions, for example, should occur at very high temperatures. So here, like if I keep continuing this, it will not go to infinity. The energy will not go to infinity, whereas nuclear fusion reactions require very, very high energy, right? As compared to vibrations of a bond or dissociation of a bond, right? So this is not explained. So the extra repulsive force which comes when you bring two atoms very close by in space, that is not explained by simple harmonic model. So we'll say the reason nuclear fusion reaction occurs at very high temperature. So now the modification of this model is called as enharmonic oscillator. So which takes into account all these problems which are described above. So it is called as enharmonic oscillator. How does it look? So this goes like vertical, and then you come down, and then you go here. So here is the extra repulsive force because the energy is too high. So it does describe that. Now here it is, this particular state is dissociation of a bond when the bond is no longer there, right? Okay. Also the difference is that at V equal to 0, V equal to 1, V equal to 2, the distance between the two consecutive vibrational levels 0, 1, 2, 3 keeps on decreasing. So now the frequencies, the differences between V equal to 0 to V equal to 1 and V equal to 1 to V equal to 2 will be at different, the energy differences will be different here, right? And also the equilibrium bond length will keep on changing. This is now my R0. And this surface is called as Morse potential surface. This is after the scientist who made these changes to the harmonic model. His name was Morse. So Morse potential surface describes all these problems which were there in the harmonic oscillator or the simple harmonic oscillator model, right? So R0 is not constant. You can see extra repulsive force. You can also see dissociation. Now, what is the surface equation? Looks like Vx equals to dE 1 minus exponential minus ax square. Okay, where a and dE are constants characteristic of a particular electronic state of the molecule. So that is clear. So now let's see what happens at x equal to infinity. So if I put x equal to infinity, I will have Vx equal to dE, right? Because now the rest of the term will go to 1. Now I can calculate my energy here, EV divided by Hc, so it will be EV. So V plus half nu bar minus V plus half square nu bar chi e and plus higher order terms which are generally omitted because those will be very small. So the rest of the terms you already know. So chi e is the only new term which was not there in simple harmonic motor, and this is called as n-harmonicity constant. N-harmonicity constant. So this will depend on multiple things, right? Now if I calculate from here, from v equal to 0 to v equal to 1, if I calculate delta E, it will be nu bar minus 2 chi E nu bar V plus 1, where V is the vibrational quantum number of lower energy state from where the transition is originating. Lower energy state. Okay, so now you have delta E. You can also calculate the population difference between V equal to 0 and V equal to 1. So you can calculate V equal to 1 and V equal to 0. Right? This can be now given by E minus delta E V equal to 1 minus E V equal to 0 divided by KT, right? Now if you put in all the values here, you will get that this is approximately equal to 0.008. This is the ratio, so it tells you the population difference. This will be equal to this 0.008 at room temperature 300 K. Okay, so we call V equal to 0 to V equal to 1 transition. So similarly, you can estimate what will be the population difference between V equal to 1 to V equal to 2, right? That will be very, very small. So that means if the population difference is very, very small, the intensity of that vibrational line will also be very, very weak, right? So V equal to 0 to V equal to 1 transition is called as fundamental transition. And is very intense. Okay. Also, if you notice that even at V equal to 0, molecule will have certain energy. So at V equal to 0, even though we are saying that the vibrational quantum number is 0, all molecules have a minimum of the 0 point energy, and this is a consequence of the uncertainty principle. Again, we are not going to go into details of this, but it's just to mention that at v equal to 0, the graph is not touching the value 0. There is some energy which is there, right? Okay. All right. So also when these vibrations are happening, the molecule is still rotating, even though you will not observe a pure rotational spectrum for a molecule which does not have a dipole moment, but molecule is still rotating, right? It has some energy, so it will keep on rotating. So you will never observe a vibrational spectrum, a pure vibrational spectrum in itself. So, but you will observe, typically vibrational lines are always observed with rotational lines. So we write, often one observes combined vibrational rotational spectrum. So a combined set of energy levels, so is given by rotational plus vibrational, is given by B J plus 1 plus V plus half H, or nu bar, we'll just write in the same units. So that means we'll have H by C over here, right? Divided by H by C. Nu bar minus X E V plus half square nu bar. So this is in centimeter inverse. So we will have H by C over here, right? All right. Or we'll just write in, we'll not write anything here because we had H by C in within B, right? Okay. So the idea is to just have the centimeter inverse units. Okay. Now we can always calculate now the delta E between different levels, between different J levels and different V levels, right? So now let us look at a transition between V equal to 0 to V equal to 1. So for every vibrational level, there are some rotational levels, right? Because at each vibrational state, a molecule is rotating. So those rotational levels will correspond to that particular V. So let's say this is V equal to 0 and V equal to 1. So at this V, I will have different J levels, like this, right? Similarly, this V equal to 1 also, I will have some J levels, which are rotational levels. So these are the J values: 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Now my possible transitions are delta V equal to plus minus 1. So I'm going from 0 to 1. So all these transitions will be allowed, and delta J has to be plus minus 1, right? So let us see, if I go from V equal to 0 to V equal to 1, from 0 to 0, so that transition is not allowed, right? So I will not draw this line 0 to 0, but I can draw the line from 0 to 1. So this line, right? So now this is the allowed transition. Similarly, if I go from 1 So I'll have to land up to 2, because my delta J also has to follow. The rotational, remember the rotational spectrum had the selection rule as delta J plus minus 1. So 3 will be like this. So now it is also possible that I can go from 1 to 0, because delta G here, delta J is equal to plus 1. So similarly I can have delta J is equal to minus 1, because plus minus both are allowed, right? Now 1 to 0 is allowed, 2 to 1 will be allowed, and 3 to 2 will be allowed, and 4 to 3 will be allowed, right? So all those fine structures will be present in the fundamental transition, which is v equal to 0 to v equal to 1. Now this set of, and the line which is not observable will be like this. Okay, so this is not observable, which is 0 to 0. Similarly 1 to 1 is not observable, 2 to 2 is not observable, and so on. Now typically these lines all are called as R lines, and these lines are called as P lines. So P band or R band, and the Q band is the one which is not observed. Okay, now if you see here, this can be numbered as R0. So basically 0 or the subscript is the vibrational quantum or the rotational quantum number from where the transition is starting. So this line will be R1, R2, R3. Similarly here this will be P1. There cannot be any P0, because you cannot go from 0 to minus 1. There is no minus 1 rotational state, right? So P2, P3 and P4. Now why we are discussing this? Because if you notice, or you can actually calculate the distance between the frequency distance, I mean distance between R0 and P1 is 4B, right? So if you know B, again you can go back and calculate the bond length, because from B you can get the moment of inertia. From moment of inertia you know the mu, which is the reduced mass, so you can calculate R, right? And difference or distance, we have used the word distance. Distance between consecutive R and P bands to B. Okay, so R0 to R1, R1 to R2, and so on. So P0 to P1. So these are 2B values, and the central two lines will be 4B. So this can be very easily now. So B can be very easily measured, and you can calculate the bond length. So even for the molecules which are not having dipole moment, so vibrational spectrum can get you the physical properties, right? So this is the introduction for vibrational spectroscopy, and next class we'll be discussing another spectroscopy, which is Raman spectroscopy, and then we will go to atomic motions. So that is all for today. See you in next class.